on page 85, we're going to read through these theorems, see if we can figure out what they're talking about. In the complex numbers, theorem 1. In the complex number system consisting of all real and imaginary numbers, if p of x is a polynomial of degree n, where n is greater than 0, with complex coefficients, then the equation p of x equals 0 has exactly n roots, provided a double root is counted as 2 roots, a triple root is counted as 3, and so on. What the heck are they talking about? Did anybody pick that up from your speed reading?
Yeah.
What are you looking
You did get it? I'm looking at Theorem 1, the fundamental theorem of algebra. Fundamental, that's a big claim.
Fundamental?
I don't know that it's the fundamental theorem. That's a bit much. You think you did understand?
Hello?
That's $1 million.
That is about $1 million.
Why are you laughing?
Yeah, you just lost $1 million.
I would be crying.
Okay, so they're saying if the degree of the polynomial is n, then the number of roots that the number of answers the polynomial have is n. So in this case, how many roots would this have? 4. Now, if it's, did you get the part about the double roots and the triple roots?
Yeah.
A double root counts as 2 roots, and a triple root counts as 3 roots, 3 answers. So it's possible we only have 2 answers.
What does the triple root look
On the graph?
like?
On the graph it looks like this. That's what I was talking about. Like number
Oh,
1
that was a double.
on Friday was a triple root.
No, double's just a U.
Double roots, remember, hit the graph and they bounce.
What about 4? 4 just crosses.
4 would be a very flat double root, like,
Oh.
oops, I missed. Like that, just flatter. And the same thing with the 5th root,
It just gets more flat.
flatter.
It is a flatter.
But you're not going to be asked that about that. Anyway, what was I talking about? Oh yeah, here. So you could have 2 double roots, for example. You could have 4 normal roots, 4 normal. A root is like an x value that makes it equal to 0. It's the same as a 0 of the function. It's a solution for this equation. So assume there's going to be 4, might end up being less. Okay, complex conjugates theorem. The short version of that is if a plus bi is a root, then a minus bi is a root. So you remember when we did the quadratic formula and we got answers like 3 plus or minus 2i and stuff like that?
Yeah.
That's basically what they're saying. If 3 plus 2i is a root, you know 3 minus 2i has to be a root. So they always go in pairs. So if 3 plus 2i is an answer, you know 3 minus 2i has to be an answer. These are called complex numbers because they combine a real number with an imaginary complex. And then similarly, the third theorem, which they didn't name any of the other ones besides the first one, first two, is that if a plus square root of b is an answer, a minus square root of b is an answer. So same thing, if 3 plus square root of 2 is an answer, then 3 minus square root of 2 is an answer. Same thing, like from the quadratic. Somebody proved this is true. I don't know how they
Was
did
it
it.
Einstein?
No. Einstein actually wasn't, math wasn't his strongest suit.
I thought he was.
Yeah, yeah.
Like he was good at math, but he didn't.
His strongest attribute was his imagination, which he used to do science. All right. And let's see, Theorem 4 says if p of x is a polynomial of odd degree. So degree, again, is basically that largest power. The degree of this polynomial
Is true?
is 3. So if it's an odd degree, you're going to have at least one real root. Now sometimes when you do a graph, if it never crosses the x-axis, it's going to have a couple, this would have a couple of imaginary roots. But if it's an odd power, remember when we did the graphs and I put them all on the board over there? A second power looked like a parabola, a third power looked like that usually, fourth power looked like this. Remember that? Fifth power. So odd powers, they started down and ended up. Or if you flip it, they started up and ended down. So an odd power has to have at least one real root, because it's going to cross the x-axis at least once. But if it's an even power, it might be floaty and have no real roots. Never equals 0, unless you use an imaginary number. Which doesn't really count. Okay. Theorem 5. Oh gosh, this is the mess one. Theorem 5 for equations. So let's see, the sum of the roots. What does sum mean? So they're saying if you have this giant polynomial, I'm not going to write all that down. If you have this big polynomial, the sum of the roots, if you add all the answers together, always ends up being the opposite of the second coefficient over the first coefficient. That's nuts that even works. That's not possible. That's random. I don't know how they figured that out. So for example, do you guys see where I read that? Let's say this is our polynomial. So if I knew what the three answers were, and I added them together, it's going to be negative 4 over 3 if I added all the answers together. So it's 4/3 or 1 1/3 if you add the answers together. If you multiply, so down below that, it says the sum of the roots is blah, blah, blah. And then it says the product of the roots is, if you multiply, it's going to be the last coefficient over the first coefficient. If you have an even power, this is an odd power, so that wouldn't work on this one, but like negative 1 over 3. If this was x to the 4th, negative 1 over 3 would be the product of roots. If you multiplied all the answers together, you should get that. And if it's an odd power, I think they just make it negative, right? Yes, it's negative that. So that'd be positive 1/3. If the degree is odd. So the answer to this equation, the answer is, if I multiplied all three of them together, it should be 1/3. If this was like an x to the 4th, it should be negative 1/3. It's kind of weird. Actually, if this was an x to the 4th, and there is no x to the 3rd power right here, the second coefficient would be like 0. So, does that make sense? Like, remember when we plug in zeros with synthetic division? Okay, something very important is written on page 87, that little red thing. I'll rewrite it. X squared minus sum of roots, x plus product of roots. So remember when we factored? Like, for example, this one. If I factored that, what does it factor to? X minus 4x plus 1. So notice that, and my answers are 4 and negative 1, right? So notice if I did the sum, these are my two roots, these are my answers. If I did the sum of these two, it'd be 3. So minus 3 goes right there, like this is like adding these together, but the opposite. Oh, was that a plus up there? Yeah, it was supposed to be a plus. And then the product, if I multiply 4 times negative 1, equals this one. That happens every time. So if they tell you what the answers are, like let's say the answers are 5 and negative 2. There's 2 ways I could find the equation. Guys, sit up. There's 2 ways I could find the equation. I could say if those are the roots, then x minus 5 and x plus 2 would be my factors. And I could FOIL this together and get an equation that has these 2 roots, right? Or I can use this little formula right here. This only works, by the way, if it's a quadratic equation. It's got to have 2 roots, basically. So if I plug in negative, the sum of the roots is 3. So I just put a 3 right there. And the product of the roots is negative 10. I just put a minus 10 right there. See how it works? Works both ways. If you know the roots, you know the factors. If you know the factors, you multiply them together to get the equation. Or you can use this formula, which if you add these 2 together, that number minus that number goes right there, plus the product, if you multiply those together, it goes right there. So anyway, you can just look at the picture. I'm not sure you guys will remember this formula. I feel like we can remember that better, probably. But this makes it kind of easy if you just plug stuff in. Clear as mud?
Yes.
Perfect. All right, let's jump in. See if we sink or swim.
Well,
Yeah.
we're jumping into the lifeboat right of water, so.
No, we just did the lesson. Okay, number 1. Tell whether each statement in exercise 1 through 8 are true or false. Justify your answers. So this is going to be theorem stuff, like which theorem says it's true, or give a counterexample. Some cubic equations have no real roots. True or false?
False.
A cubic equation has a degree of 3, which is an odd power. So there was one of the theorems said an odd degree will always have at least one real root, because it's basically this thing. It's got a odd powers start up and start down and end up, so that has to cross at least once. Which theorem said, so it's false. Which theorem said that?
First one. Second one.
If it goes down forever and up forever, it has to touch. Odd powers always do that. Like to the 3rd power, it basically has to look like this. So it has to touch eventually.
Theorem 4.
Theorem 4. So put false, theorem 4.
How did you figure
Theorem 4 is the one that talks about odd degrees having one real root.
Are you gonna do that again?
For true false, I guess I will. Okay. Number 2, every polynomial equation has at least one real root.
False.
Okay, it's false.
Theorem 2.
No. We have to give, there is no theorem that says
You could say 4.
that exactly. Not quite. 4 says odds do, but it doesn't mean inverses don't. Anyway, we have to give an example of where that's true. And get a clean sheet of paper here. Do you guys know how to write an equation where you get imaginary numbers? We need it to be an x squared equation.
X squared equals 21x minus 7.
You know. Okay. If this one won't work. How do I
be writing.
Well, this will be imaginary. So this is my proof. This is my argument to show that that's a false statement. If I solve this for x, what's going to happen? You're going to get, what would the answer to this be?
Squared.
Plus or minus square root of negative 1, or plus or minus I. So that's two imaginary answers. So this equation right here is just a counter example.
So
It
it's,
has 0 real roots, so that shows that counter example.
So it's false?
Yes, false.
what are you supposed to write for that, for the reason?
The counter example.
You write that equation?
Yep. Most of these are the theorems, but some of these aren't. Number 4, the roots of a certain fifth degree equation are blah, 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 blah. Is that possible? Well, okay. Do you guys see the problem? If 1 minus square root of 2 is a root, what else must be a root?
What, are you doing 3 or 4?
3. If 1 minus square root, oh, sorry, I was looking for what my.
Oh, it
Whoops,
should be 1
my
minus.
bad. Okay, number 3. The roots of a certain quartic equation are plus or minus 1/2, 0, and 1 plus I.
It should be 1 minus I.
If 1 plus I is a root, 1 minus I is a root. And how many roots would that give us? 5, which is impossible in a quartic. Remember, quartic meant 4. So they didn't, that's kind of combining two theorems. They didn't write the theorems, they just said 1 minus I must also be a root.
Which is false.
Yes, it's false. They didn't go into in-depth explanation, and I'm cool with that. That's fine.
What is your example for the explanation?
1 minus I must also be a root. I guess they implied that they've listed all the roots. So. Okay, number 4, kind of the same thing. The roots of a certain fifth degree equation are blah 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 blah. What's the missing root that that should be there?
1 plus square root of 2.
1 plus square root of 2. So it's kind of the same thing as the last one. Just put 1 plus square root of 2 should also be a root. Okay. 5. It is possible for the graph of a cubic function to be tangent to the x-axis at x equals -2, 1, and 6. What does tangent mean?
It kisses.
So when a line is tangent to a circle, for example, it brushes up and hits at one point. You guys know that from geometry? So when a graph is tangent to the x-axis, whoops, it was like that. So what kind of root was this?
No.
It's a double root. So they're basically saying there's a cubic function and it has 3 double roots.
That's impossible.
That would be like 6 normal roots. A cubic function can only have 3 roots. What did they put for the reason
That's
for
not
that?
true. Or false.
3 points of tangency imply a degree of at least 6. Right, because we have to have at least 3 double roots. It could be a 4th root and be really like flat, but anyway, yeah. 3 double roots implies a degree of at least 6. Number 6, no polynomial equation can have an odd number of imaginary roots.
That's false, I would say.
True.
That is true. Remember, anytime there's a complex or imaginary answer, it's always like a plus or minus.
Yeah.
So they have to come in pairs. So that is true. Which theorem said that you have to have for every a plus bi, there's an a minus bi? It was no. That's not 3 is not imaginary.
Oh, two.
Is it 2?
Yeah, it was 2.
But was the answer 6?
It's true.
No.
Because it's theorem 2. Number 7. Suppose p of x is a polynomial with rational coefficients. Do you guys remember what rational means? Do you remember what coefficient means? So many terms. Take for granted. Do you remember what rational means, Rachel?
No.
It's not like 1/3.
No, it is like 1/3 or 3 or rational is anything that can be written as a over b, where a and b are integers, so it can be a fraction, it can be 3 over 1 or just 3. The only thing that is not rational is like square roots,
Pi.
imaginary. Okay, coefficients are the numbers on the front. These are coefficients. 1, -3, -10, those are coefficients on the front of the term. What was I? 6, 7? 7. P of x is a polynomial with rational coefficients, and b is rational, but square root of b is not. If square root of b is a root of the equation p of x equals 0, then negative square root of b is also a root. Is that true or false? True. Which theorem said that? Square root of b. Square root of b would kind of be like 0 plus square root of b. And if that's a root, what else has to be a root?
Zero
So
what?
your minus square root of b. So, which theorem said that? 3, wasn't it?
Yep.
Oh.
Yeah, that's 3. So that's true about theorem 3. It's kind of a mess, isn't it?
Yes.
Oh, it'll also be a 2-day, but it was 22. We're almost done. Number 8. A plus bi is a root of the polynomial equation. Okay, before I keep reading, if a plus bi is a root, then what?
A minus
A minus bi is also going to be a root. P of x equals 0, then the equation must have an even number of roots. Is that true?
Yes.
No. Because it's possible, like, a plus bi is a root, and a plus bi might be a root, and then your third root might be c, some random number. That would be an example of an odd degree, right? Looks like they put the counterexample again. So it is false. You could have an odd power. The example they used is x cubed plus 1 equals 0. Because, like, negative 1 would be an answer, but the other two answers are imaginary. Leave it at that. Okay, number 9. Find the sum and product of the roots of the given equation. Okay, the sum of the roots, if you look back at Theorem 5, is the opposite of the second coefficient over the first coefficient. You guys see where I got that from? Right there, the sum of the roots, blah, 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 is negative a sub n minus 1 over a sub n. So that's the second, opposite of the second coefficient over the first coefficient. What is the second coefficient? Negative 3. So it's negative 3 over the first coefficient is 4. What's that simplify to? 3/4. So we're saying if we knew all three answers to that equation, or two answers to that equation, and we added them together, this should be what comes out. Then it says find the product. Back at Theorem 5, if you look at the bottom, it says the product of the roots is it's the last coefficient over the first coefficient, or it's the opposite of the last coefficient over the first coefficient. Is the degree of number 9 odd or even? Even. So we're going to use the last coefficient over the first coefficient. So the last coefficient is 6, and the first coefficient is 4. So what does that reduce to?
3
3/2. So that is the product of the roots. You guys see how I did that? On number 12, I should probably warn you, the second coefficient is going to be what? 0. Because it has no x cubed. So when you find the sum, you need to do 0 over 1, basically, which simplifies. Number 11, the sum of the roots is negative second coefficient over first coefficient. So negative 5 over 3, which does not simplify, so it just stays like that. The product of the roots is the degree odd or even? Odd. So we're going to use the opposite of the last coefficient over the first coefficient.
So 2 over 3.
So 2 over 3,
Did you get the 3?
the first coefficient.
Why is it not a 2?
When you do odds, it says you have to put a negative in front. So you have to do the opposite when you're doing an odd degree. Anyway.
If the last number, like on number 10, the last coefficient would be 1, right?
So no,
It would be 0.
it'd be 0. On number 10, yeah, thanks for pointing that out. The last coefficient is a 0 because there's no constant out there.
Oh, just on 12.
For today. Yeah. So you only have 4 evens, right? We did all the others.